So power series. So in Calc 2, we had this this integral that was kind of difficult to integrate. And this is just one of many, many, many examples of things that you can't integrate. And you can't integrate it because there's no closed form function that describes this integral. Like the integral of cosine is sine, integral of x squared is e to the, no, what's the integral of x squared? X cubed over 3 or something like that. So anyways, we have actual functions for a lot of the other functions that we have. We can actually find integrals of them. But there's a handful of weird functions that we don't have integrals to. And so some of them are really common, like this one, that Mathematica and the mathematical community decided to call it something. So if you punch this into Wolfram alpha, you're going to get a function that says ERF. It's called the error function. Another one is sine t squared dt. This one doesn't have a closed form integral either, and so this has also a special function. I think it's SI or S function or something like that. And there's many others that don't have names because they're not as popular as this. And so what we decided to do in Calc 2 is to, instead of coming up with these other weird functions, they just expanded this using a power series. And it turns out that power series are polynomials, and we can easily integrate, differentiate polynomials. And so the only disadvantage there is that we'd have to go on forever if we want to get the exact value. Now the good news is that when we do calculations numerically, we don't need to go on forever. Okay, at a certain point, you know, a lot of our calculators display digits up to 9 decimal places, and that's good enough if we can go to 9 decimal places. So we can use power series expansions for things, and as long as we can get accurate up to 9 decimal places or whatever, however many decimal places you want, we can go as far as a 3rd degree or a 50th degree polynomial, and then we can stop at a certain finite point and say this is it. If you haven't already noticed, in this differential equations class, we're doing a lot of integrals. And so, in fact, there's a few integrals where they say write it in integral form because we can't integrate it. And then there's one problem that we've had where they say write it in power series form. And so a lot of these things where we can't find nice functions to solve for our differential equation, we can at least try to find a pattern to see if we can get a polynomial approximation using power series. And the approximation can go as high a degree as we want if we can find a nice enough pattern. All right, so power series around x minus a is an infinite series that looks like this. A lot of times we're going to be interested in x minus 0 or just plain x. And so I think we call that the Maclaurin series or something. Do you remember that term? It's like a Taylor series, except instead of a being a number, well, 0 is a number, we'll just let a equal to 0, and this will be just x to the n. So special case, when a is equal to 0, our power series is c sub n x to the nth power. And that's generally what we're going to be going for. And the other thing that would be good is that if you have a handful of series memorized. Convergence, interval convergence, radius of convergence, absolute convergence, and ratio test are going to be the ones that we're going to focus on here. So if you remember what you learned in Calc 2, do you remember what you learned in Calc 2? There's an integral test. We won't need to worry about that. There's a comparison test. We won't need to worry about that. There's a root test. We don't need to worry about that. So we can eliminate some of those other things that I think are a little bit more difficult to grasp. And these things, the idea of a radius of convergence and the ratio test, I think are a little bit easier to deal with. And so that would be important for us to try to remember. Now there's a special word that we're going to use. They call this in Calc 1, they call this C1 differentiable or C2 differentiable. It's the idea that you can take the derivative of a function so many times. A function is said to be analytic at a point if it can be represented by a power series. And you know, the power series kind of depends on the derivatives, right? Because it's derivatives of things, according to Taylor's polynomial formula. So power series is dependent on derivatives. So if something is differentiable infinitely many times, then we can guarantee that the power series will exist for that function. And so it's analytic. And almost all the functions we're going to be dealing with are analytic. There's a handful of weird functions that that are not analytic. Okay. Also denominators, when you have zeros in the denominators, we'll worry about that a little bit, but not so much. So error, Bluetooth. Whoops. So we should, I think I jumped in my notes here. We should worry about a handful of important series. That if you don't already know, you should try to commit to memory. So the first one is e to the x, and that's a special series that is easy to remember, I think. It goes 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And a lot of times we want to write the series in general n form, so I'll write x to the n over n factorial. And then if we want to consider this as an infinite series, we just put a dot, dot, dot at the end of the last term. And the other thing we can do, if possible, is to write it using the summation form. So we can write it with k or whatever. K goes from 0 to infinity, x to the k over k factorial. If you can convince yourself that x to the 0 is 1, and I guess what I wanted to say was 0 factorial. That 0 factorial is equal to 1. I asked, when I was a freshman, I asked this physics guy the same question, and his answer was, because if it wasn't, the gamma function won't work. And I said, okay. So every time somebody asks me that, that's going to be my answer. The factorial is a special case of the gamma function. Gamma function is a real life function where if you put integers in there, positive integers, you're going to get exactly the same numbers as what you would with a factorial. What's neat about the gamma function is that you can put fractions in there, like 1/2. So it turns out that 1/2 factorial is actually a number. Now, I don't know what it is off the top of my head, but it can be calculated. The only thing is that the gamma function doesn't have negative integers. You can't put negative integers there. You can put negative fractions in there, but it won't work. While we're at it, and since I'm wasting time anyways, just do a quick Google on the gamma function. Wikipedia is, I think for scientific mathematical stuff, Wikipedia is a fairly good resource. You know how they say you shouldn't do research and you shouldn't rely on Wikipedia? I think that's a lot of stuff in the non-sciences. The Wikipedia is a little bit more shaky. But anyways, the gamma function is related to the factorial function in this way, and the gamma function at 1, when x is equal to 1, we have 0 factorial, and that's equal to 1. So can't see it very well here, but in this graph, we see a couple of points here that are supposed to be equal to 1. And I often throw this integral in my Calc 2 class. I haven't taught that in a while. Come on. Sorry, a little rusty here. So those are both values of 1, and that's when n is equal to 1, we have gamma of 1, which is 0 factorial, and that's how it's defined. When n is equal to 2, we have gamma of 2, which is equal to 1 factorial, and that's equal to 1 also. Okay. And so, yeah, when I teach Calc 2 and we're doing integration by parts, I throw this as a special problem in where they have to do integration by parts like 3 or 4 times to get a feel for what this looks like. This gamma function is actually a factorial. All right. So given that 0 factorial is equal to 1, this is a general term for this, this exponential series. So this is easy to memorize because you're matching the power with a factorial denominator, and then it just goes from 0 to infinity. Sine and cosine, I think, are just as easy. The cosine, the thing to remember is that the cosine is an even function. So you have even powers of x. And then you're going to take them from the exponential function, and you're going to alternate signs. Is that a lot of things to remember? So all you're going to do is you're going to snag the even terms from the exponential function, and writing them in order, you're just going to alternate signs. So to express an even power, it's a little tricky, but you probably have seen this in algebra. You just multiply something by 2, and it's going to be guaranteed to be even. And I don't know if you remember in Calc 2 where you have to do the ratio test and cancel things out. You know, that's important to try to remember too. Nick?
After x, the also before factorial, would it be minus?
Yeah, it'll be minus, but so this is where it kind of gets tricky when you put dot dot dots and stuff. So I can put minus there if it looks better. Oh, so speaking of, what? Yeah, so I forgot that. Thank you. Because these things are all positive, and so including this thing. So I have to put a -1 to probably just the k power, I think. It's either k or k plus 1. So I need to squeeze that here as well. Because it depends on which term you are where it starts to alternate. So the sign is the same thing, except you're going to be grabbing the odd terms. And then, so it's also alternating, and it's just the odd terms. So x cubed over 3 factorial, x to the 5th over 5 factorial, so we have the alternating part, the positive negative, so it's -1 to some n power, and an x to the 2n plus 1. That guarantees that it's odd, 2n plus 1 factorial. So one of the things that's important to worry about is to make sure that if you have an alternating series, to make sure that you know, when you plug in like k is equal to 0, I use k. I'll try to use k. When k is equal to 0, that I have the correct sign. K is equal to 1, that I have the correct sign, positive or negative. All right, so these three series are related, and I don't know if we've talked about Dimov's formula. Is it Dimov's formula? Oh, no, Euler's formula, where e to the alpha plus beta I, the complex number, is equal to some combination of sine and cosine. So this is one way to prove it using the series. If you expand this, and then notice that the I changes from positive to negative every 2 steps. So it's not like -1 where it's -1 to the 0 power is 1, -1 to the first power is -1, -1 to the third power is +1, or second power, whatever. The I goes positive, positive, negative, negative, positive, positive, negative, negative, etc. It goes on like that. So that allows you to skip terms over here, making this positive, positive, negative, negative in your exponential function. All right, so that's the relationship between sine, cosine, and exponential function. Now there's another one that seems like it's a whole new series. But this one, another easy one to remember, you just have to remember this function, 1 over 1 minus x. And the power series for that is 1 plus x squared plus x cubed, etc. So I think that's about the easiest series to try and remember. So this one has some restrictions, though, and I didn't bother putting the restrictions up in the first three because they work for any real number that we want. So this is all real numbers for these three. So I could put any x. This is going to work for any x real number that I have. This one only works for open parentheses. So this is a little bit more restrictive, and it only works for -1 and 1, and we can't even include -1 and 1 because if I put any of those numbers in, you'll get a series that doesn't make sense. So this is known as the, anybody know what this is called? This is known as the geometric series. And if you remember how a series was done when you guys started studying series, one of the first things they talk about is geometric series, where the radius of convergence, they don't explicitly say radius of convergence, but this is centered around 0, and the radius of convergence goes between -1 and 1. And you can see that if you put 1 in here, you break off and you get 0 in the denominator, so we know that's bad. But it turns out if you put -1 in here, was that the bad one? No. So if you put -1 in here, you get 1/2. So it seems like it should work. But if you put -1 into the series over here, you'll see that it won't work. And so what's even more interesting is that it breaks off at 1. You know that when you put 1 in for x, it's bad. It turns out that you can't put anything else beyond 1 or -1. So when they talk about a radius of convergence, it converges within a certain interval, and anything beyond that, even if you only have one bad point, so this is your bad point, and it's going to converge everywhere else except for that bad point. Now what's going to happen here is that anything outside here will definitely diverge. So in studying the radius of convergence, that tells you that your radius is a distance from your center point out to the first time it breaks. And if it breaks here at 1, then it's going to break at -1 also, and nothing else beyond that is going to work. So that's the whole idea behind the radius of convergence. And then the interval of convergence can also have something to do, because this one didn't work at 1. It may or may have worked at -1. In this case, it doesn't work at -1. But any derivation that we get from here might also work. So what I want to say now is that from here, you can come up with other series by taking derivatives or taking integrals. So for example, 1 over 1 minus x quantity squared, you can get this by taking the derivative, right? So if you take the derivative of the series, you'll come up with this new series. ln of 1 minus x. You can do that by taking the antiderivative. So I want to say that you should be able to derive from the geometric series, you should be able to derive other series that may or may not look familiar. The series for 1 divided by 1 plus x squared, instead of doing the Taylor series, Taylor polynomials to find a pattern, you can think about this as 1 over 1 minus, and change the x in all these points in the series to negative x squared. So if you do that and change all these points into negative x squared, then you have the exact same thing that we were looking at. The tangent inverse then can be derived from here. This is just the integral of this thing so you can find a Taylor approximation, a series approximation for the arctangent as well. So because all these other series that I just wrote down come from the geometric series that has a radius of convergence of 1, the radius of convergence for all these are also going to equal to 1. Now what's different about that is that the interval of convergence may change. And so some of these may have different intervals of convergence. And when I say interval of convergence, it's a matter of looking at negative 1 and 1 and determining whether to shade them in as part of the interval or not. And I don't recall the interval of convergence for the rest of them, but I do know that the interval of convergence for the tangent includes the endpoints. And some of these may include the endpoint or may not include the endpoint, but regardless of how they come up, the radius of convergence is still going to be 1. Okay. The arctangent function, by the way, is defined for all real numbers. So if you use a series, then you're only restricting your series to negative 1 and 1. Otherwise, you can try to come up with a different series for the arctangent. You put negative x squared into here, and then you integrate it term by term. Yeah. Well, you just write them like you're adding them all up, but you're not going to add them all up. Well, let's actually find a series for the arctangent while we're here. Let's go on a new page. Whoa. So let's find a series for arctan. And we'll try to remember that the arctan comes from the integral of 1 over 1 plus x squared dx. And 1 over 1 plus x squared come from the power series of that. So let's start with, let me just rewrite our power series for 1 over x, which is 1 plus x squared plus x to the third plus x to the fourth. Let's just leave it at that. I'll just put dot, dot, dot. So if I want to replace my series with a different x value, so I'm going to write it kind of tediously here. And then simplify it. So this becomes a 1 minus x squared. Negative is a positive. We got x to the fourth. And then negative x to the sixth plus x to the eighth. And you can kind of see a pattern, I hope. The pattern of how this goes. We just have even powers, but depending on what your sign is, you'll see it. And then now we're going to integrate this. term by term. So the antiderivative of 1 is x. Antiderivative of x squared is x cubed over 3. Antiderivative of that is x to the 5th over 5. So it becomes all odd powers. No factorials here. So here's your power series. Now, the interesting thing to try to do is to see if you can write this in a summation form. So let's see. We have alternating. We have an alternating series, so we're going to have a negative 1 to the k power. When k is equal to 0, I want it to be x. So positive. So this looks like it'll work just with the k power. And now I have x to an odd power, maybe 2k plus 1 or minus 1. I think plus 1 would work because when k is equal to 0, I have x to the first power, and that's the first term. And then the denominator just matches, so 2k plus 1 with no factorial. And then I've written this as the arctangent. That's the power series for the arctangent. Again, you can derive this by doing Taylor polynomials, finding derivatives, dividing by stuff, and doing all that other stuff. But this would seem a little bit quicker. Okay? All right, getting flashbacks from Calc 2? Power series. Let's look at this differential equation. It's always nice to start off with something that you already know the answer to. And I hope when you're looking at this, you already know the answer to this. Or at least know how to do it, right? What would you, we're just fresh off of the second order differential equations and stuff like that. How would you solve for this? This is the first order, by the way. And so what? No. I mean, yeah, you can, but auxiliary equation what? Separable. This is separable differential equation. So remember, the stuff that you learned in the first part, those are the easy ways to solve differential equations. So if you have a first order, think about the easier ways to solve the differential equation. The second order stuff, that stuff that's where it gets a little bit more complicated. That's where you include the auxiliary equations and then do the solutions and stuff. But if you have a first order differential equation, think simple. Separable first. If it's not separable, then you hope maybe it's a linear differential equation. This is actually also a linear differential equation, so you can use the integrating factor to solve for these things as well. So, so try not to forget the first couple of chapters in this, because you'll be tested on it in the final. But aside from that, it'll just be good for you to remember it, because I came from Professor Lapuz's class. I don't remember anything. That's not a nice thing to hear. So, separable differential equation. It might have been better if it was written as dy dx plus y is equal to 0, so that you can think about this separable differential equation. It's also what's that called? When you just have all just the dependent variables. There's no independent variables in here. Anybody remember what that was called? Autonomous differential equation. It's also an autonomous differential equation. All right. So if we separate this, we get dy over y is equal to dx. Should I continue? Do you guys remember what the answer is? I think I have a negative in here somewhere. So ln of y is equal to x or something like that, and then you take the e of both sides. So y is equal to e to the negative x times a constant. So this is our old familiar exponential growth and decay. Okay? So if we want to think about this as a power series solution, let's see if we do come up with this exact same e to the x business. Okay, so let's see how we solve power series. What we're going to do to solve power series is we assume a solution is of a form of a power series. So I guess we, instead of assume, we just say let y equal to a power series. And the power series has general form. If you looked at the first page of the notes, power series is c to the c sub k, x to the k power. And we're assuming that this is a power series centered around the origin. And we're going to do most of that assumption, assuming that it's based around the origin, just to make our calculations easy. Otherwise, we can assume that it's based around 1 or pi or a different number, like a, and then we'll work on the same thing. It'll work the same way, except our calculations would just be a little bit more difficult. But if we assume everything's at 0, we can always do the offset to 0. So we're going to assume that our power series looks like this. So I hope you'll get good at taking derivatives of the power series that look like this. But for now, for the first time we're doing this, let me expand it out. What does this mean? This means your power series actually looks like c sub 0. And by the way, to solve for a power series means to solve for c sub 0, c sub 1, c sub 2, etc. Okay, so you're solving for these unknown constants. So c sub 0 times x to the 0 plus c sub 1 times x to the first plus c sub 2 times x squared plus c sub 3 times x cubed, etc. So that's what this power series is saying. Now, the only other y term that we have in our differential equation is y prime. So let's we need to find y prime, which means we need to take the derivative of this. The derivative of this is 0. That's gone. C sub 1 plus 2 c sub 2 plus 3, oops, c sub 2 x to the first power plus 3 c sub 3 x squared plus, and then we go on forever. Okay? So I'm going to leave this blank for now. Oh, I guess we should try to figure it out now. Let's try to figure it out now. How does the summation look like here? Looks like c sub 1 is my first term. Right? Oh, wait. Let's take a look at this. Let's take the derivative of that. And we took the derivative term by term, right? So this is term by term. Let's take the derivative of that. What's the derivative of this thing? K c sub k x to the k minus 1. Perfect. Wait, is it perfect? K starts from what? 0? 1. K could start from 0 if you want, but when k is 0, this whole thing is 0, so it's not really all that important, is it? So here, this is another point that's going to be important for you to remember when you're doing these problems is when you take derivatives, the indices will move. Now the difficult part is that you're going to want the indices to match up or the powers to match up or both. you're going to want something to happen. We'll see what's going to happen. All right, so now we kind of have two ways to do this. One way to do this is to spread them all out like this, expand them all out, and then put them into this equation and see if you can find patterns. The other way is to use the series. So we're going to be using the series. So let's see how that works. So we got y prime plus y is equal to, it's equal to 0, but let's see how this is going to work out. It's equal to the sum, this is y prime. Where's y prime? K equals 1 to infinity of k c sub k x to the k minus 1 plus y, which is the sum, k goes from 0 to infinity, of c sub k x to the k. Now again, it's a little bit easier to work on this if we spread it all out, because what we're going to want to do is kind of match the powers around. So let me write down, since we have the expanded forms here, let me write down the expanded form for y prime, which is c sub 1 plus 2 c sub 2x plus 3 c sub 3x squared plus, I'm going to go one more. This should be 4 c sub 4 x to the third, right? So that's y prime, and y is c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, and then I'm good with that. And the idea is to match this up. It looks like I have a couple of constant terms. I can pair them up. C sub 1 plus C sub 0. And it looks like I have a couple of linear terms. I'll match that up. This is 2 C sub 2 plus C sub 1 times x. The quadratics. And the cubics. Okay. So much like what we would do with solving equations and stuff, this is all equal to 0. So all these coefficients should all equal to 0 as well. Before we do that, though, let's see if we can rewrite it in terms of the summation sign. How do you suppose we do this? It looks like this, right? Any ideas what goes inside? K times C sub K minus, no, C sub K minus 1. Does that work? Oh, look, it's KC. Oh, is it? I changed it to minus. I don't know why. Anybody watching the World Series? I just KC's on, so. Yeah, so we need to see.
It will be k plus 1 c of k plus 1 plus ck.
How about if we started with 1? How about if we subtract 1? Does this work now? That's right, Vanessa's idea anyways. Say it again. But say it again. K plus 1. C. K plus 1. So it is the same thing. In other words, we can write this a bunch of different ways by changing the index, changing the power, and changing the subscripts. So that's what's gonna make this a little tricky, because you can write it several ways. And what I'm kind of interested in is for you to not look at this middle part. And see if you can go from this to one of these two. So that's going to be the tricky part. All right? We'll talk about that in a minute, but let's continue on with this thing since we're solving for this. And we're saying that this thing is supposed to be equal to 0, which means the coefficients have to be equal to 0. So when you're doing this problem, usually if you're doing like a second order differential equation, you would have been on one page already. So on the next page you would continue on this problem. And so you would now assign, depending on which of these summations we're going to use. Let's choose this one where k is equal to 1 first. When k is equal to 1, you will have 1 times c sub 1 plus c sub 0 is equal to 0. Is that correct? Because you want all these things to equal to 0. So when k is equal to 1, my coefficient is going to be 1 times c sub 1 plus c sub 0. And that should equal to 0. When k is equal to 2, you will have 2 c sub 2 plus c sub 1 equal to 0. K is equal to 3. We have 3 c sub 3 plus c sub 2 equal to 0. Okay so far? Now, c sub 0 is our first constant, and so we're probably going to want things in terms of c sub 0. What I mean by that is you're going to say c sub 1 is equal to negative c sub 0. So c sub 0 will remain your arbitrary constant, will become your arbitrary constant, and all the other constants, c sub 1, c sub 2, c sub 3, etc., should be able to refer back to what c sub 0 is. Or should be written in terms of c sub 0. What does that mean? That means c sub 2 plus I'm sorry, I want to just say, I want to just solve for it real quick. Negative c sub 1 divided by 2, right? So, well, this is positive, but if I'm solving for this when it's set equal to 0? Yeah. So c sub 2 is going to be, let's replace this with negative c sub 1 or c sub 0. So it's going to be positive c sub 2, c sub 0 over 2. Okay? And then c sub 3 is equal to c sub 2, negative c sub 2 divided by 3, which means c sub 3 is equal to, what's c sub 2? C sub 0, so it's negative c sub 0 divided by 2 times 3. Right? Now, if we haven't yet figured out the pattern, we can continue just trying a couple more to see if we eventually get the pattern. But if you do get the pattern, c sub 4 should equal to what? Positive c sub 0 divided by 2 times 3 times 4, right? And c sub 5, negative c sub 0 over 5 factorial. Okay? All right, so now that we've gotten a good handle on the pattern, let's plug that into our solution. Our solution is supposed to be this. This is supposed to be our solution, right? We could just jump out and get the general n here. C sub k. What's c sub k equal to? Any guesses? Be negative 1 to the k. C sub 0 over k factorial. So when k is equal to 0, this is positive. Does that work? When k is equal to 1, this is negative. Does that work? It looks like it works, right? So maybe we can just put that down over here. K goes from 0 to infinity. We have negative 1 to the k, c sub 0 over k factorial. That's c sub k. And then don't forget the x to the k. All right, let's write it out. When k is equal to 0, this is c sub 0, right? When k is equal to 1, this is a negative. This is c sub 0 times x. When k is equal to 2, this is positive. C sub 0 over 2 factorial x squared. When k is equal to 3, it's negative. C sub 0 over 3 factorial x cubed. When k is 4, this is positive. C sub 0 over 4 factorial over x to the 4th. So it looks like it all has a c sub 0. So let's factor out a c sub 0. And it looks almost like the exponential function, but it has positive and negative alternating. Anybody know why that is? So imagine putting a negative x So imagine putting a negative x wherever you see an x, right? So this is exactly the exponential function with, instead of just a plain x, it has a negative x. I think, hey, that's our original answer. Yeah? Yes, if we would have worked with this thing, we would get the same result.
Now we are working with that.
With which one? This we did it this way. If we did it this way, we would have gotten the same result.
So in that example, we start with k equal to 1, right?
In this case, yeah.
So then, but then you say in the linear solution is k equal to 0.
Yeah, because that's our original assumption here. Okay, this thing just came after we put into the differential equation. After we put in the differential equation, we moved the index around. So what we're going to practice, like I said, what we're going to practice is going from here to here without doing all this other stuff. And that's what you need to get good at. That's what you're going to practice over and over again. We'll do it. Next time we'll do the same thing, except we won't write down the terms. We'll just take a look at it. If we need to, we'll write down the terms just to see, just to help us visually with it. But otherwise, we should be able to go from the differential equation to a simplified power series with the differential equation. All right? Wow. Question? Yeah.
Would it be simpler just changing the index and then manipulating
Yes.
it so that you can then put the two together because they're linear operators?
That's exactly what we're going to do. So what we're going to do is we're going to do some index changing. And whenever we change something in the index, we're going to change something in the body of the sum. And just for, sorry, I keep moving up. But just for a quick reference, here this is 1. And here the index starts at 0. So the starting point starts with 1 versus starting with 0. And look at how the k's change. This is k minus 1, k minus 1. So if we change the index down to 0, we add 1 to each of the k's. K plus 1, k plus 1. We add 1 to k minus 1. That just gives us k. And then k up here. So we're going to need to be flexible with shifting the index and then changing how the inside of the series looks like. Okay? All right, so I think that's it for today. Tomorrow or on Tuesday next week, we're going to dive into, we'll do one more first order example, and then we'll dive into second order And then we'll just keep digging at this power series business. All right, see you guys next time.